in the notes, we've derived an eigenvalue problem for the magnetic field. The question is, can you also derive a generalized eigenvalue problem for the electric field? And while you're at it, can you figure out if the operators A and B involved in that generalized eigenvalue problem are actually Hermitian or not? So pause the video and try to answer this question. Starting point, as usual, are of course Maxwell's equations. So let's start by writing those down. So we have the curl of the electric field is equal to minus j omega mu and then the magnetic field. And of course, we have a second equation for the magnetic field that looks like this. E. Okay, what we want to do now is try and derive an equation where only the electric field figures. So let's look, for example, at the second equation and let's try to eliminate h. Now we can get h from the first equation. So here we are going to replace h by the curl of the electric field divided by minus j omega mu. So this is going to be our left-hand side, and then for the right-hand side, we have j omega epsilon. And let me stress here that epsilon is a function of the spatial coordinates, so it's not just a constant in our case, times the electric field. Cleaning this up a little bit, bringing some constants to the right-hand side, we have the curl of the electric field is equal to omega squared mu, and then epsilon as a function of r times e. Now what we did in another exercise is we moved this epsilon here to the left-hand side, and then we had a regular eigenvalue problem for the electric field, but that eigenvalue problem turned out to be non-Hermitian. Question is, if we leave it in the following form, we do have indeed a generalized eigenvalue problem, because this is then our operator A, and over here we have our operator B. So remember, epsilon is not a constant, so we cannot fold this into the eigenvalue. It's actually an operator, multiplication by this function over here. So now we have this generalized eigenvalue problem with two operators A and B. And the burning question is, in this particular case, do we have Hermitian operators for A and B? Let's check that. Let's first focus our attention on our operator A. Now, in order for this operator to be Hermitian, we need to start from, for example, the operator operating on the second factor over here. And we need to try and move this operator, this curl, so that curl operates on F. And if we get the same result, then we have a Hermitian operator. Now, something we used a lot in the notes and in many exercises is that we can peel off one layer of this curl. We can move one curl operator to this first factor over here. But the price we have to pay for that is an integral over the surface. But as usual, we're going to restrict ourselves to situations where that integral vanishes, either because the fields at infinity vanish or because we're dealing with periodic functions. So now we can repeat that trick again and peel off the final layer of our onion and move that to the first factor. And then indeed we see that we have now our operator curl operating on F. So we have the situation where our operator A is Hermitian. Good news. Let's now look at operator B. Is that operator also Hermitian? So then we have to have the situation that F epsilon times G is equal to our epsilon operating on F first. Can we move that epsilon? Well, just a quick reminder of what this actually is. This is shorthand for a volume integral of F times the complex conjugate of epsilon G dV. Now, the only way we're going to be able to move that epsilon outside of the complex conjugate so that it can join F over here is if epsilon is real. And that means that we have to deal with lossless media. But if we have lossless media, then we can safely move the epsilon to the first factor. And in that case, we do have a Hermitian operator, but only if we're dealing with lossless systems.